Yeah, thank you very much, Gauthier, for the introduction. Yeah, I'm Hugo. I'm currently a postdoc at Hong Kong University. I mean, I'm joined between the Niels Bohr Institute in Copenhagen and the University of Hong Kong. And I'm doing astrophysics. So astrophysics is is interesting because you get to give a lot of outreach talk for people who have no knowledge in science or in math. So I gave a lot of them, and of course, as a researcher, I do a lot of scientific conferences. So on the other side, I've been to academic conferences with astrophysicists. But it's the first time I get the chance to give a presentation in front of people who are not astrophysicists, but have a strong knowledge in math and machine learning. So it's a new exercise. I'm excited to do that, and I hope that you will learn something. Yeah. So I'm going to present a paper that I published with collaborators about 2 years ago. The idea is to detect galaxy mergers in the sky, but maybe for some of you have no knowledge about the universe. So let's just start with a quick map of the universe. So you know where we fit when we do this kind of project and exercise. So you probably know this small scale for astrophysicists. So you have the sun and the 8 planets of the solar system. I like this image because it's to scale. So this is the solar system. And basically, we're going to grow up in scales. So to go from the center of the sun to the outer part of the solar system, it's about 4 billion kilometers. And I mean, the numbers are stupidly high, so we just change units when we do astronomy. And instead, we use light hours or light years. So this is the distance that is traveled by a photon in 1 hour or in 1 year, provided that the photon travels at 300,000 kilometers per second. So it means that basically to go from the center of the sun, I mean the surface of the sun to the planets, it takes about 4 hours. It takes 8 minutes for information to go from a photon that is emitted on the sun and that arrives on Earth. It takes about 8 minutes to come. So if tomorrow, if now the sun, well, I mean, depends where you are in the world, but if the sun switches off, you see it 8 minutes later. And if you convert this into light years, it's about 5 × 10⁻�3. So for now, these units are a bit weird, but you will see that it will make sense when we go up. When we go farther from the sun, we look at local stars. We are in the solar neighborhood, and you see that we already grow in scale, and now light years, so kilometers are completely useless, light hours are completely useless, and light years, they start to make sense. So basically, again, it takes 150 years for a photon to go from one side of the box to the other side of the box. Probably you know that Alpha Centauri or Proxima Centauri, so this is the closest star to us. So there is a projection effect. I will come back to this on this image. So it's not a real image, of course. But yeah, it takes about 4 years for a photon to go from the sun to the closest star. And if we continue growing in scale, so we fit all these stars into a galaxy. So in our case, this is the Milky Way. Of course, this is not our galaxy because we are inside, but this would be a good, this is another one. But this would be a good representation of the galaxy, like a spiral, beautiful spiral galaxy. And the sun is in the outer part of this galaxy, roughly 80% of the disk radius. And now you see that even light years, they start to be a bit high numbers. So it takes 50,000 light years to go from one side of the galaxy to another side of the galaxy. So when I'm studying galaxy merger, these are the kind of objects that I smash. I mean, I want to study when this object smashes into another object of the same kind. What happens? Can we detect them in the sky, etc.? But we can keep zoom out, of course. So the Milky Way is in the local group. So now it takes 5 million light years to go from one side of the box to the other side of the box. For the astronomer, if you have a telescope and you are in the southern hemisphere, you can see the Andromeda galaxy or the Magellanic Cloud that were used in the past by people on the boats. Yeah, so this is the local group. And again, this is not the end of the story. We can keep zooming out, okay? And we have the large-scale structures, and now the numbers are completely crazy, 450 roughly for this. It's not an image, again, it's a simulation. I will come back to that later, but 450 million light years. So this is 450 million years to go from one side to the other of the box. And here, each dot that you see is a group of galaxies, okay? So you have these filamentary structures on the very large scale that we call the cosmic web. And at some places, for instance, here you have a lot of galaxies within the center, very massive galaxies, and in the filaments you can find all the galaxies of the universe. So if you are an astrophysicist, you are not working on all this. You are, specialized in what scale. So some astrophysicists, they study planets, okay, and they're going to use kilometers or light hours maybe to discuss. Then, if you go to larger scales, this is a topic of this talk. You have galaxies, so light years, and thousands of light years, and on the even larger scales, you have the large structures, millions of light years. A unit that is usually commonly used by astrophysicists, and I will use later in this talk, is called the parsec. So it's a length unit. Okay, you use parsec to measure length, and you see that the size of the solar system is going to be 0.1 milliparsec. The size of galaxies, 15 kiloparsec, and the scales of larger structure, 150 megaparsec. Two comments. This large-scale structure, 150 megaparsec, it's not the size of the universe at all. But just if you go to larger scales, you keep having this filamentary structure. You don't see you don't see any difference. If I were to show you an image on a gigaparsec, for instance, it would look very similar. It's just a change of scale. So we will focus on galaxies, and I want you to remember this 15 kiloparsec. So this is a typical radius of the Milky Way, 10 kiloparsec, 15 kiloparsec, depends who you ask. So to go from the center to the outskirts, 10 to 15 kiloparsec. Remember this number because it will be useful later. So again, the goal of the project was to have this kind of objects and you smash it into another one. What happens? Can we find them in the universe, etc. So when you're doing astronomy, you have in research in astronomy, you have two possibilities. Either you use telescopes and you try to understand the real universe. In this case, you are an observer. This is not my case. I'm more a theorist. And so basically, I never touch telescope and I use a computer. And so to study this problem of galaxy mergers with computers, what you can do is to run a simulation. So I don't know how familiar you are with simulation, but basically, I assume this is a picture, and these are what we call the initial conditions. So you know the density everywhere in space, you know the position of every stars everywhere in space, you know the speed of every stars everywhere in space. You have also gas, and you know the temperature of this gas, you know the composition of this gas, if it has a lot of metal, if it has a lot of hydrogen, for instance. You know the magnetic field everywhere in space, what is the strength of the magnetic field, what is the direction of the magnetic field, etc. So if you start with a picture, this is what we call the initial condition. And then we've had physicists since a few hundred years now, and they have understood how these properties they evolve with time using a differential equation. So you have all these quantities which are coupled in partial differential equation, and you can so you have a set of differential equation which you've probably heard about. So hydrodynamics, it It allows you to study how gas evolves or fluids in general. So it can be used if you want to understand the flow around an airplane, or if you want to understand waves, or even gas in galaxies. You have gravity, which tells you how objects attracts to each other, general relativity. So it's useful if you want to understand the expansion of the universe, for instance. Thermodynamics, which explains you how the heat transfers from one direction to another. Electromagnetism, which expresses how the magnetic fields lines change. Maybe some chemistry if you want to form some molecules, some radioactivity if you want to understand the decay of elements, etc. So you have all these differential equations, and with initial condition and differential equations, you can integrate forward in time, and you can follow, you can know what will happen to these two galaxies. So here's you have a projection of stars, and you have two black holes, and you integrate forward in time, and you just go in a supercluster in France, in my case, and you run the simulation, and you just let it evolve. Okay. The idea is that you can smash a galaxy, two galaxies in your computer, and you can then print the data, the position, velocity, temperature, etc., of every galaxies, every stars at each time step, and you can measure quantities and study the effect of the merger onto these quantities. So let me give you an example from this paper, Hello 2015. I told you there are two black holes, and you can, for instance, look at the separation between the two black holes in kiloparsec as a function of time. So you see that the initial separation is about 100 kiloparsec. You remember I told you the size of galaxies is 10 kiloparsec, so initially the galaxies are far away. But you smash the galaxy, and the two black holes, they get closer, 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 until they are super close, and they have formed a binary. So what you can say with this kind of simulation is that when you have a galaxy merger, it's likely that you form a supermassive black hole binary. And this was predicted from the early work of Mitch Spiegelman in the 80s. And this is very important, actually, to use this kind of simulation to study in which condition you form a binary, what are the properties of the binaries, the masses of black holes, how fast they rotate, etc. Because there will be a satellite launched by NASA and Europe in 2034, which will detect the mergers of these black holes. The second thing that you can look at, for instance, is how much gas is flowing onto the black hole. So here I'm showing the black hole accretion rate. So in solar masses per year, so how many masses of gas fall onto the black hole in 1 year. And you look at that as a function of time. And you see that when the black holes are at pericenter, so at their closest approach, you have an enhancement of the black hole accretion rate. So this is a log scale. And this is one thing that you can say also is when you have a galaxy merger, you expect to have luminous black holes. So luminous black holes, it's important to know about them because we launched a satellite, JWST, in December. And this satellite will look at this kind of black holes. And the last thing that you can do with this kind of simulation is to look how many stars are formed per unit time. So how many stars in solar masses per year are formed as a function of time. And similarly to black holes, you find that when the galaxies are at pericenter, you have a star burst, so a lot of star forms. So when you have a galaxy merger, this triggers star formation rate. And again, this was predicted by the early work in the 90s. The idea is that when you run this kind of simulation, you have a complete knowledge of the system. So you know the position, etc., as a function of time of everything. And so you can measure these quantities as a function of time, and you can see how they evolve and what are the effects of the galaxy merger onto the different quantities that are black hole separation, black hole accretion rate, or star formation rate. But you see that the issue is that when you're doing astrophysics, the time scales are very large. So here the simulation is integrated forward in time for about 2 gigayears, so 2 billions of years. And this is a problem because if you make an observation, so here you're looking at M51, you take a picture and you come back in 50 years, okay, that is longer than your career. You take the same picture and it's gonna, you look at the same galaxy and it's gonna be the same picture. because the time scales are much longer than human time scales. So when you are doing observations, if you want to understand galaxy mergers, you have a temporal problem because you cannot wait long enough and measure the quantities as a function of time. But there is another problem which is inherent to astronomy in general, is that galaxies, they move in space, so you need 3 coordinates, x, y, z, and they have a relative velocity, vx, vy, vz, and so this is a 6D problem. But you cannot turn around galaxies. And here, for instance, you have the blue dots and the green dots. They appear to be very close, and they appear to be much farther from the orange dots. But if you were able to turn around this system, you would actually realize that the orange dots and the blue dots are close, but the green dot is actually very far. And this is a projection effect, which you always find in astronomy. So basically, this is the problem. If you have a galaxy pair, you see 2 galaxies in the sky. Okay, you don't know if they are close. This is the only information that you have. Can you design an optimal strategy to know if the 2 galaxies will merge? So Gauthier suggested that we look at the image entirely, but this is too complicated for me. I'm doing astrophysics. I'm not a machine learning person. So what I'm just going to do is assume that the 2 galaxies are simple points in space and say, okay, is the distance, the projected distance in the sky is smaller than a given value, then I will say, okay, these galaxies will merge. Let's be a bit more fair. Actually, we have access at the projected distance in the sky. Okay, so we look at the angle between the 2 galaxies, and we also have access at the radial speed. Okay, so the reason is because the universe is in expansion. Galaxies are going away from us, so we have access to the radial speed. So we have 2 quantities. The radial speed, which is delta, which we know z, or delta z for the relative radial speed, and then the projected distance in the sky. Okay. And maybe you are assuming if these quantities are smaller than some threshold, and the threshold may depend on the mass of the galaxies or other quantities, then these galaxies will merge. The question is, what is the best threshold? What is the optimal threshold? And of course, you want to say we can actually measure them with machine learning. We can try to design an algorithm. I mean, the algorithm will be very simple, and we have to optimize to find what are the best thresholds. And this is where machine learning fits in this project. So I want to say I'm not doing machine learning in particular. It's just that I wanted to know what it was about machine learning. So I was curious about this project, and so I started to investigate machine learning and see how we can solve this problem. So there is one issue. What about the training set? I told you, like, you don't know if so this is a real image. Okay, this is M51, and you don't know if these galaxies are merging. So I mean, you can know because you have tails here, etc. But in general, you don't know if 2 galaxies are merging for the reasons that I explained earlier. So how can you do? And the idea is actually to use the numerical simulation. And so this is where I'm very good at, which is running numerical simulation and understanding them, etc. And this is the idea, to run a numerical simulation, prepare mock data, train the algorithm on the mock data, and then observers, particularly, they will use the algorithm to actually understand real images in the sky. So how do we do? This is basically the goal of the paper, was to build the algorithm, to build the data set and to build the algorithm to be able to detect galaxy mergers. So the idea is to run a simulation for which I told you have access to the temporal and the spatial informations. And so for this, I use a very big simulation, state-of-the-art cosmological simulation. So you have 150,000 galaxies. The simulation has been run on 4,000 CPUs during 1 month. So you block the supercluster Oxygen, which is a French supercluster for 1 month, and you store the position and velocities, etc., of all the stars regularly. So that's a very big data set in the end. And because this kind of simulation is cool, I can show you a video. So you see, this is when you evolve forward in time. And I told you here, every dot is a galaxy. Okay. So you see that we can follow the evolution of these galaxies as a function of time. And you recognize, so this is an inset of this region of the universe. Okay. And you recognize on the large scale the cosmic web and the filamentary structure. Once you have run this simulation and you know the position, velocity, masses, etc., of these galaxies as a function of time, you can move from the series view to the observer view. So by chance, this had already been done in 2017. So the simulation has been run in 2016, and in 2017, these guys they made a make image. So this is how the sky would be if we were living in this universe. Okay, so this is not a real image. The goal is to move from the series view, where you have access to X, Y, Z, being the position, Vx, Vy, Vz, being the velocities and time, to the observer view, for which we have access to theta phi, so the two angle, and Z, which is a redshift. And again, the Z here is not the same as the Z here. So it's sorry about the confusion. But the idea is again to move from the observer view, for which you have access to everything, to the series view, for which you have access to everything, to the observer view, which is limited, but which is what we have access in our real universe. And I want to stress that this fake image is a very representative of our real universe. So this is a real picture of our universe from Cosmos 16, the catalog Cosmos 16, and you can see that, of course, there are some differences, but if you look at these images statistically, you compare them statistically, you can find that they have similar properties. Then you want to map the two views between the observer perspective and the series perspective. So say you have a galaxy in the sky of the observer. It corresponds to these galaxies in the series view. You have this galaxy in the observer view. It corresponds to this galaxy in the series view. So this had been done by Clotilde L'Aigle in 2017. And finally, this is where I came. You follow every galaxy pair. So for instance, you have a galaxy here, here, and here in the observer view. You can map them in the series view. So they happen to be here, here, and here. And because this series view, you can evolve forward in time, you can know that, for instance, the blue galaxy and the red galaxy, they will merge at some point to form the purple galaxy. On the other hand, the orange galaxy is very far and it will never merge, and it will never merge with these other galaxies. So you can construct like that a very big catalog where you have a lot of pairs, okay? And you know if the pair is merging or not, and if it is merging, how long it's going to take for the pair to merge. So you end up with this 1 billion pair catalog, and you have some observable, the projected distance in the sky, the redshift difference, the mean redshift, the masses of the galaxies, mass ratio, star formation rate, etc. So these are quantities that if you look in your telescope, you have access to them. And the quantities that we have access because we are using a numerical simulation, but that observers do not have access because they cannot wait long enough. It's the merging timescale, so how long it's going to take for the galaxy to merge. And first, we just focus, we want to know, are the galaxies going to merge or not? So when you have this catalog, you can start to look at the very simple quantities. If you want to know if galaxies merge, it's a very difficult problem because on 1 billion pairs that we have, there is 100,000, that is 0.01% of the pairs that merge. So it's a very unbalanced problem, highly unbalanced problem. 0.01% of the galaxies merge, and the rest is not merging. And the other issue that we have and that we found, we didn't know that actually until so the fact that it's unbalanced is kind of expected because you can look at galaxies and usually pairs are very far. But the thing that we didn't know until we analyzed the catalog is that it's a very degenerated problem. So for instance, here I'm showing different pairs. And you can look at pair 1 and 2, and you see that they happen to have the same projected distance in the sky. They happen to have the same redshift difference, but one of them is merging in 2 gigayears, and the other one never merge. Even though they have the same quantities, the same properties, they have a different fate. And similarly, pair 3 and 4. So pair 3, they happen to be, they look to be very far in the sky, but they merge very fast. And pair 4, it looks to be very close in the sky, and it takes a very long time to merge, 6.5 years. And if you actually look into the simulation to understand why this happens, so I'm showing here the relative distance, the distance between the two galaxies as the function of time for every pair. And the dot corresponds to the moment we catch the galaxy pair. And the issue is that if you catch the galaxy pair at a pericenter or an apocenter, you can see that there will be differences. So the result depends on the moment the pair is caught. And again, this is a very big problem because when you are looking in the sky at your pair, you cannot wait. Even if you wait, the picture will be the exact same. So with these two problems in mind, we still tried to understand if we could classify these pairs using the data that we had access to. And we started very simple with the idea that I explained to you earlier, with simple thresholds on the distance and the redshift difference. So if the redshift difference is lower than some threshold and the distance is lower than some threshold, this is a merger. If it's one of the two parameters is larger than the threshold, it's not a merger. So it's not a decision tree, but it's similar to a decision tree. And the question that we wonder is, what are the optimal thresholds? And if you want to find an optimal threshold, you need to optimize on some metric. And the metric that you may think about immediately is precision or accuracy, which tells you among what is the fraction of selected pairs which are truly merging. So if you are selected, your algorithm tells you, okay, I have this amount of, I've selected this amount of pairs. What is the fraction that is truly merging? And you can look as a function. So I'm showing a color map here. So the color indicates the accuracy, and you have the threshold in redshift difference here, and the threshold in projected distance here. And if you take very selective threshold, so say you say the redshift difference has to be very small, and the redshift difference has to be very small, and the projected distance has to be very small, then you will not select a lot of pairs. Okay, so but most of them will merge, and you see that the accuracy is very high. But your completeness or recall, it will be very low. So the completeness, it's the fraction of truly merging pairs which are selected. So the issue, if you take very restrictive thresholds, is that you will miss most of the pairs. So your completeness will be very low. And vice versa, if you take very loose threshold, your completeness will be very high. You will select all the mergers, but your accuracy will be very low. So, I mean, when I did this exercise, I realized that you really need to look at the confusion matrix, right? When you do this kind of exercise showing the number of true positive, true negative, false positive, false negative, and if you balance on the accuracy and the completeness, it's not necessarily a really good idea. And if I looked a bit deeper in the literature, so both these parameters are important, but they evolve in different directions. And if you want to optimize on one metric, you may want to combine both. So there is the F1 score, which you may have heard about. But I found that the Matthew correlation coefficient, so I don't know if you are aware of this metric, according to some for binary class classification, it's the best metric. It's basically a combination of true positive, true negative, etc. And you see that the Matthew correlation coefficient, you can do the same exercise and optimize on the Matthew correlation coefficient, and it shows nicely some maximum for a redshift difference of 10 to the minus 3. And for a projected distance of 100. So now you can go to your friends who are observer and tell them, okay, these are the optimal values that you should take. The MCC is 0.38, so the higher the better. Okay, and what is cool is that 100 kiloparsec. If you remember, the size of galaxies is 15 kiloparsec. So it's typical of like 10 galaxy radii. So this is the number that you are expected, but we show that this is actually the best value. Now, I told you that maybe the thresholds may depend on some parameters. So because we have access to the masses of galaxies, we can look at the mass of the primary, and we can do, so we split the sample in masses, and we do the exact same strategy as before. And so here I'm showing, for instance, so in blue, the blue dots on the left axis are the optimal threshold for the distance as a function of the galaxy mass. And on the right axis, it's the optimal redshift difference for the square as a function of galaxy mass. And you have the MCC, which depends on the galaxy mass. Of course, you can compute it. And if you look at the overall MCC, it's 0.4. So it's an overall improvement of 0.02, which is, I was a bit sad when I saw that. But what I was happy about is that if you look at the evolution of these optimal thresholds as a function of the mass, you find a power law, which is 0.2 or 0.28. And from theoretical arguments, so with pen and paper, you do back of the envelope calculation, you can show that these parameters, they should scale as 1/3. So it's very nice because we found with machine learning these optimal parameters, and with a kind of first principle and physical arguments, we can understand the scaling. So this makes us very confident in the selection process and in the catalog in general. And finally, because I told you I had never done machine learning prior to that, I was like, let's use all the parameters. So I have 9 parameters and just do a multilayer perceptron. Train the multilayer perceptron. We have 1 billion pairs, 100,000 which are merging. So we should be able to do something good. And here I'm showing a histogram. So this is the number of pairs, okay? And this is the output of the network. Basically, it outputs a number between 0 and 1. 1 being I'm 100% sure that it's a merger, and 0 meaning I'm 100% sure it's not a merger. And there are 4 lines. We will go one by one. First, because the dataset is very unbalanced, of course, you want to use a balanced dataset to do the training. So I downsample the number of non-mergers, and I train the dataset. And then on the validation set, I use a balanced dataset. So these are the 6 lines. And you see that if you look at the orange line, so this is the true mergers in the balanced dataset. You see that most of them, actually, you have more than 90% of them which have an output which is larger than 0.95. And if you look at non-mergers in the balanced datasets, you have more than 90% of them which have an output lower than 0.05. So if you look at the MCC for this catalog, you have MCC of 0.97. So this is excellent. The network works perfectly. You are very much able to distinguish between galaxy pairs and, between galaxy pairs which merge and pairs which not merge. But if then you go to the unbalanced dataset, which is more realistic because this is what you will find in the universe, these are the thin lines. If you look on, so the red thin lines, these are the true mergers, and you can see that again, you have 90% of them which have an output which is larger than 0.95. And if you go to non-mergers, so this is in green, you have again 90% of them which have an output which is lower than 0.05. So again, if you give the algorithm a merger, it's very likely that it tells you it's a merger. If you give the algorithm a non-merger, it's very likely that it tells you it's a non-merger. But the issue is that because the problem is extremely degenerate, you have a very small fraction, actually 0.35% of the non-mergers, which have a very high probability of merging. And this 0.35%, it overcomes the merger. And in the end, the MCC is only 0.41. So it's not much better than the simple technique. And so again, the problem is that the dataset is extremely unbalanced and degenerated. I couldn't find a solution to make this work, but if you have any suggestion, I'm very much open to that, how to deal with this kind of problem where not only the problem is unbalanced, but it's also very degenerate. So we stop here with the conclusion. I hope you learned something that, at least about galaxies, that are important if you want to understand galaxy evolution, because they trigger star formations, they trigger black hole accretions, they lead to the formation of black hole binaries, etc. That it's very difficult from an observational perspective to know if two galaxies will merge, because you cannot wait, because these processes they take decay years, and because you cannot go around the system to see what is the speed, what is the real position, etc. I hope that I showed you that we can use this kind of cosmological, hydrodynamic, and numerical simulation, which is essentially physics laws, and then you integrate these laws forward in time to build mock catalogs of galaxy pairs, and we know the fate of these galaxy pairs, so we can go from the series view where we have all this information to the observer view where we have our real universe. That this problem of classification is difficult because it's not only unbalanced, but it's also very degenerated. I derived some simple mass dependence thresholds, etc. We understand very well their value and scaling, 100 kiloparsec, typical of galaxy size, scaling as a power law to the 1/3, which is consistent with theoretical expectations. Actually, this neural network, it works a bit better. Okay, the MCC is better than for the very simple threshold. But honestly, to me, it doesn't. It's not worth I mean, it's very simple network, but it's not worth the fact that we lose the value which we had understood with physics. So with all this, I will stop. Thank you very much for staying, despite the fact it's not finance. And I hope you learned something, if not in machine learning, at least in astrophysics.